Hello. In this chapter, overall, chapter 3, we're going to be talking about polynomial functions in general. That's things that look like this. And so I'll wait until the next section to talk more about what a polynomial is and point out what's going on here. But in this particular section, we're going to start out the chapter by talking about a specific kind of polynomial function, which is quadratic functions. So a quadratic function is a function like this, ax squared plus bx plus c, where the a, b, and c stand for any numbers. The only restriction is that a can't be 0 because then we wouldn't actually have an x squared term. So basically, a quadratic function is a function that involves the variable being squared, but nothing more complicated happening than that. So here's one example of a quadratic function. Y equals -4/9 x squared plus 24/9 x plus 10. This came from an example or a problem I found in a book, and I'm not going to take the time to look at it in detail, but it's supposed to represent the path of a diver who jumps off the end of a diving board into the water. And as we'll see, quadratic equations describe paths or graphs that have this kind of a shape to them. They go up and come back down, or they go down and come up. But things like a baseball or a football, after you hit it or kick it or throw it, follow a path a lot like that. So that's one thing that quadratic functions are used for, to model motion like that. Okay, so here are some more, maybe simpler quadratic functions. If you just have x squared, that's a quadratic function. It's the simplest quadratic function there is. And so we already know what that looks like. X squared minus 4 counts as a quadratic function. X squared plus 2x plus 1 would be a quadratic function. Negative 2x squared plus 1 is a quadratic function. And in each case, the graph of these functions is what we call a parabola. It's either the kind that opens upward, and then the turning point, what we call the vertex, would be the lowest point on the graph, or it's the kind that opens downward, and then the turning point would be the highest point on the graph. So either way, that vertex is kind of right in the middle of the parabola, and if you drew a vertical line straight through the vertex, that would cut the parabola in half, and the two halves would be mirror images of one another. So the parabola would be symmetric with respect to that axis of symmetry, that vertical line that runs right through the vertex. And you know whether your parabola is going to open upward or downward based on whether the coefficient of x squared is a positive number or a negative number. Let's look at some more examples of quadratic functions. Now, remember in the last chapter, we talked about if you start with one of those basic parent functions and then do various things to it to transform the graph in various different ways, to shift it up or down or right or left, or reflect it across the x-axis, or stretch it, or things like that. So if we just start with the function x squared, the graph looks like this. It's a parabola that opens upward. Its vertex is here at the origin at 0, 0. How would that change if we had x minus 5 squared plus 1? Remember, replacing x with x minus 5 shifts the graph 5 spaces to the right, and then adding 1 shifts it 1 space up. So it's the same shape, but It looks like that. 3 times x minus 1 squared minus 2 would look like if we started with the graph of x squared, multiplying by 3 will stretch it, make it taller and narrower, kind of 3 times as narrow, and then shift it 1 space to the right and 2 spaces down. So it looks like this. Notice it is narrower, and the vertex that used to be at 0, 0 is now over here at 1, negative 2. What would negative x plus 2 squared look like? The negative reflects the graph across the x-axis. It flips it upside down, and then replacing x with x plus 2 shifts it 2 spaces to the left. So we get something that looks like this. Flipping it upside down didn't change where the vertex was, but then when we shifted it 2 spaces to the left, the vertex is now here at negative 2, 0. And what about x squared minus 4? If you just start with x squared, you'd have to shift it 4 spaces down to get the graph of x squared minus 4. So these are all parabolas. They're just parabolas that maybe are stretched or inverted or shifted somehow. And the way I have these written here, they're not all in that ax squared plus bx plus c form, but I could get them in that form. If I want them to actually look like ax squared plus bx plus c, I could multiply things out. Like I could take x minus 5 squared and multiply it out as x squared minus 10x plus 25, and then add 1, and that would be x squared minus 10x plus 26. Same function, just a different way of writing it. Algebraically equivalent. Remember, when you take a binomial and square it, you get the first thing squared, you get the 2 times the first thing times the second thing, and you get the second thing squared. So these others can be multiplied out and written in the form where you've got an x squared term and an x term and a constant term, so they do look like this, ax squared plus bx plus c. Now let's take a closer look at one of them. How do we get from 3 times x minus 1 squared minus 2 to 3x squared minus 6x plus 1? Or how would we get back? How would we go the other direction? Well, if you start with x minus 1 squared and multiply it out, that's x squared minus 2x plus 1. So then 3 times all of that would be 3x squared minus 6x plus 3. And so 3 times all of that minus 2, if we take that and subtract 2, we get 3x squared minus 6x plus 1. So that's the algebra involved in going from this to this. Now what if we started with 3x squared minus 6x plus 1? What if we started with the function in that ax squared plus bx plus c format? How could we go from that to this? Well, it would involve completing the square. Here's how that works. I would take these first 2 terms, the x squared term and the x term, and from just those 2 terms, I would factor out the coefficient on the x squared term, that 3 there. So I would write it as 3 times x squared minus 2x. And then I've still got the plus 1 on the end outside the parentheses. Now, inside the parentheses, I want to complete the square. I want to add a number that would make this a perfect square. We learned about completing the square back when we were using it as one way of solving quadratic equations. Remember, the trick is to look at the number in front of the x, take half of that number, and square it. So here, half of this squared would be 1. So I added 1 inside the parentheses to make this a perfect square. X squared minus 2x plus 1 is just x minus 1, the quantity squared. Now, this wasn't an equation that I could add the same number to both sides of the equation. But what I can do to keep everything equal to what it was before is come along and subtract the same thing I just added. If I add a number and then immediately subtract that same number, I haven't changed the value of the whole expression. So when I added 1 inside the parentheses, it was getting multiplied by 3. So really I was adding 3 times 1. So if I want to keep everything equal to what it was before, I would have to subtract 3 times 1. So that's why I put this on the end, minus 3 times 1, or just minus 3. So here we have 3 times x minus 1, the quantity squared, and then plus 1 minus 3 is minus 2. So that's one way you can tell from something like 3x squared minus 6x plus 1 what the graph looks like, where the vertex is, how it's shifted, that sort of thing. You can go through this process of transforming it into this a number times x minus a number squared with another number on the end. And then you can see, oh, that's like x squared, only stretched by a factor of 3, shifted 1 space to the right, and then down 2 spaces. So that is one way of figuring out what's going on with a quadratic function. Where's the vertex? What does the graph look like? Stuff like that. I'm also going to show you another way. But what we were just looking at, where we had that 3 times x minus 1 squared minus 2, that's an example of this kind of form, this standard form for a quadratic function, where we have some number times x minus some number squared plus some other number. If you see that, you know what it's going to look like, because you know the graph is going to be a parabola. It's going to be a variation on just x squared, only it's been shifted over h spaces horizontally and k spaces vertically. So the vertex, instead of being at 0, 0, would be at the point hk. Now, if it really is x minus a number and then plus a number on the end, those would both be positive. But if it says x plus a number, you can think of that as minus a negative. And if it says minus a number here, you can think of k as negative. So the vertex has coordinates h and k, each of which could be a positive number or a negative number. And then this number a out in front here tells you which direction the parabola is opening and sort of how it's stretched. So if a is a positive number, then you have a parabola that opens upward. And then you would have a minimum at the vertex. That would be the lowest point on the graph. If a is just 1, it would be the exact same shape as just plain old x squared. But if a is some other positive number, like 2 or 3 or 1/2, it would be stretched or squished. And if a is a negative number, then you get a parabola that opens downward, and then the maximum would be at the vertex. That would be the highest point on the graph. So in the example we were looking at, the a was 3, the h was 1, and the k was negative 2. So this would be a parabola that opens upward, because a is positive, and has a vertex at 1, negative 2. And that's where we have a minimum. F of 1 is negative 2, and that is lower or less than f of anything else. Another example we looked at was negative x plus 2 squared. There the a would be negative 1. The h would be negative 2. If you want to think of this as x minus a number, that number would have to be negative 2, and the k that's added onto the end is 0. So the vertex is at negative 2, 0. It opens downward from there, and that's the maximum.